Assalamu alaikum, hello everyone and welcome. In this video we are going to explore how to efficiently formulate a linear quadratic LQ optimal control problem. Before we dive into the core formulation, we need to understand specific matrix structures and operations that make this process possible. The most important tool in our kit is a special matrix operation called Kronecker product. Its symbol is a circle with a cross inside. Let's look at how it works. Suppose we have a matrix A with m rows and n columns, and another matrix B of any size. The Kronecker product of A and B is defined by taking every individual element of matrix A and multiplying it by the entire matrix B. For example, the element A11 is multiplied by B. A12 is multiplied by B, and so on, until the very last element, AMN, is multiplied by B. In MATLAB, it is very simple. You just use the function kron A, B. Let's look at an example. If we do symbolic calculation for the matrix A equal sim A %D, and we take the matrix 3 by 5. This is our matrix A. We take sim, the matrix B, and we simply do kron A, B. Or we can take a matrix B two by 3, and we can do kron multiplication. We notice here that A11 is multiplied by the matrix B, and A12 is also multiplied by the matrix B, and so on. We have the dimension of the answer, the number of rows of B multiplied by the number of rows of A, which is 6. And the number of columns multiplied by the number of columns is 6 by 15. Next, let's talk about identity matrix I. As you likely know, an identity matrix of size n, In, has ones in its diagonal and zeros everywhere else. In MATLAB, you can generate this using the command in. If we go to MATLAB, write I, for example, 4. This is the identity matrix of size 4. And we can use also sparse matrix SPI to reduce time. 4. We can get the full matrix, full, by writing full answer. However, for LQ problems, we often need to shift the diagonals. If we want to move the diagonal upward, we use positive offset index k equal 1. If we want to move the diagonal downwards, we use negative offset index minus 1. We denote this as INK, where n is the size and k is the position of the offset. If we go to MATLAB, we use sparse matrix M equal 6 and Z equal sparse M by M. Sparse meaning zeros. All elements are 0. We get full Z, get all elements zeros. If we use D equal ones, M, this is row vector, column vector. We use sparse diag. D, this is K equals 0. This is the main diagonal, and Z. We get full answer. This is the main diagonal. If we offset upward, we can write this 1, k equal to 1, and we get full and downwards we put k equal minus 1. Now let's combine these ideas to create block diagonal matrices. This is a matrix where submatrices like A1, A2, A3 up to AN are placed along the main diagonal. An efficient way to build these is using the Kronecker product. If you take a matrix B and find its Kronecker product with an identity matrix, B will be placed on the diagonal n number of times, where n is the size of the identity matrix. We can simply write in MATLAB bulk diag and put here the number of times of matrix B. If we go to MATLAB and define ISPI for, we take identity matrix 4 and bulk diag B 4 times. This is the bulk diagonal, and we can construct this by using kron. Then kron I B. The same answer. As we move forward formulating the LQ optimal control problem, we will encounter even more specialized structures. Offset block diagonals. By taking the Kronecker product of a matrix A and a shifted identity matrix. You create a matrix where A is placed as an offset and diagonal rather than the main one. We can do this using MATLAB. M equal 6, Z equal sparse, M by M, and D equal ones, now we can generate the identity matrix like this: full, SP diags, D in the main diagonal 0, Z. This is the identity matrix, and we will place, we take this matrix, we'll place kron, this identity matrix, and for example B. This is in the main diagonal. If we can shift it by taking here -1, for example, or +1, or we can shift it by -2. Now, if your structure requires negative matrix, you can simply apply a minus sign to the Kronecker product operation. For example, like this. We can Kronecker product in with B, and here is a minus sign. Sometimes you will need a combination of these. For instance, you might have a matrix with an identity on the main diagonal, for example, while another matrix A is shifted by one position. This is represented by combining a standard identity matrix with a shifted Kronecker product. We can do it in MATLAB. For example, this is shifted Kronecker product, and we can add identity matrix. We copy this, the identity matrix main diagonal, here's 0. Of course, there is an error. We have to take kron product here to match kron product of the identity matrix. The dimension mismatch, we can take here the answer is 12 by 18. So we can add here sparse identity matrix SPI, and we take the dimension 12, 18. Okay, this is the main diagonal, and here the shifted matrix. Understanding these building blocks is the key to mastering the efficient formulation of the control problem. Thank you very much.